Okay, my friends, this is exciting. They have started to react to my evidence showing that particles are made of dipoles, and they're still trying to maintain the standard model. It's not working. So this is their response, and here's my response to their response. Okay, my friends, I've done several videos about Jefferson's lab and their experiment trying to create electron showers and hold back the muons. And here is, they had just come out with this recently. Experiment pinpoints gluon mass inside of protons. All right, because originally, see these little colored balls there? These are what they call quarks, and they say that's what's inside of the standard model. But now they're saying new stuff points to what I proposed to them and to everybody for the last 10 years, that everything is made of dipoles, and the dipoles are gluons. A gluon means a black and a white ball attached together. Okay, here's the key. They are looking, the whole purpose of all of these different things is to figure out what protons and the building blocks of all matter is. So here's what the really basic statement is. Jefferson Lab researchers probed the nucleus, the little core in the center, to find out at what distance and energy scale the nucleus ceases to appear to be made of individual nucleons and instead appears to be made of quarks and gluons. All right, think about this. They want to know where inside that nucleus. So let's say this is the nucleus. In my world, this is exactly what the nucleus is. And here is where it turns into what they're looking for is the gluons. That's a gluon. It's just a little tiny bar magnet. Now for them, they have quarks. I don't. All I have is gluons. In dipole electron flood theory, gluons make everything there is. And a gluon is a positive and a negative. It's the bright glowy part attached to the black ball. Okay, so let's go through this. This is Jefferson Lab, and this is what they say is inside of a proton. And this is their explanation of it here. The reason we're going through this is because this article came out today. Beyond the visible universe, new research reveals how gravity influences the quantum realm. Right now, they don't know what gravity consists of. They can't account for it according to the standard model. I can account for it very easily, and I can actually show it to you. Now, this is Thomas Jefferson National Laboratories, and I believe I worked with them, and I'm going to show you, I think it was them. Well, I know I've tried to contact them. But anyway, this is what they're saying there. Nuclear physicists have discovered gravity's profound influence on the quantum scale. Well, like I say, nobody even knows what gravity is. It's revealing the strong forces distribution within the protons for the first time. That's what I show, is the strong force of the black, which the white just desperately wants to be attracted to that black. Just unbelievable amount of suction against that black. However, we were able to divide them, as I showed here. Before I go any further, I just want to show that we can divide those. And we did it right here. The black and the white were together, and we separated the white from the black. And here's what it looks up real close. Going through that Venturi I just showed you right over there. There's the Venturi. That's it right there. And the black ball detaches from the white. This is exactly what they want to see. And to do this requires just a ton of energy. Where do you hear, I mean, literally tons of energy to pull the white away from the black. And that's all you want to do to create electricity, is to make the white become separated from the black. That's exactly what we did. All right, so let's just continue on here. So they say they have discovered gravity's profound influence, and all gravity is the black attracting the white, or the white wants to go to the black. The black seems to have no preference other than to just the white wants to attach to it instantaneously. Now, all right, so here we are back at Jefferson Lab. And they say they discovered how gravity's profound influence on the quantum scale shows the strong force for the first time inside of protons. And again, I showed you what they think is inside of protons. I'll show you what is inside of protons. Groundbreaking research combining historical theoretical insights with modern experimental data. Yeah, I had this idea in 1970, and it was dipole flood theory. It offers unprecedented understanding of the proton's internal dynamics and sets the stage for future discoveries in nuclear science. Absolutely. And that is what dipole electron flood theory is nothing but dipoles that make up the nucleus. Now I'm going to show you what they have to say about their nucleus and how they're trying to wiggle it in somehow into the standard model. It's not going to work. Okay, here's my claim. That right there is gravity, and so is that. And these are the glowy particles, which are the very energetic particles, and they so desperately want to be attached to that black that you just almost can't rip them apart. To rip that white away and put it into a battery, that's what's called electrical generation. To rip that away takes a lot of energy. And you put it in a battery, and it doesn't increase the weight of the battery at all. It gives it a lot of energy. These have no weight. The whites have no weight. Now, all you're going to be hearing about is gravity. But the standard model does not explain gravity. I have no idea how gravity works. If they use the standard model, it just doesn't work. The standard model does not work. All right, these are the two particles, the only two particles that exist. They are always stuck together in nature. You can't rip them apart. Except if you do make an atomic nuclear explosion where, yes, or you put it through a venturi like we did. Now, that has all the energy and no weight. That has all the weight and no energy. This desperately seeks ground, which this is. That is ground. It's all the weight. It's dark matter. It's the muon. That's what it is. Now, this is what's going to change from the standard model. The standard model is not made out of quarks and all those other things they're talking about. It's made of gluons. And we were able to separate these two particles. These two particles are the same as these. Now, you always have gluons, and they're called Dirac neutrinos. I will show you that. Two of these gluons together, which is an unstable particle, that is an electron, basically. We always thought of it as an electron. A negative particle has all the attraction and the charge, and it bounces, and it attracts to dark matter. So this is the energetic part. The black is just a carrier, and they used to call it the carrier boson. I don't know why they stopped. Anyway, the two of them together make up what we would always consider an electron. Electron's not stable. It won't stay by itself. An electron will find something to glue onto, like a photon or a particle or something like that, or become heat. It will infuse itself into heat. So if you take something like this, my buddy here's Caesar, and he weighs a pound, and it's a certain temperature in here. When the temperature changes, it goes cold, or he loses electrons. They leave because they have a colder place to go to. Electrons are energetic. They want to find a cold place to attach to. So they will move towards the cold, and this will become cold. If it's hot in the room and I bring this in and it's cold, the electrons that are excess in the room, because that's what heat is it's just excess electrons. That's all it is. And they will find their way into here, and then everything will get into the same ambient temperature. They'll all be the same temperature, everything. This will be the same temperature, but it takes a certain amount of time. And that's what we used to have to do, is leave the weights in the weights and measures for 24 hours for them to be the same temperature as the weights and measures. That's the way there. They had an exact same number of electrons in them as all the rest of them. They weren't trying to get any away, and they weren't trying to take them on. So everybody was the same. You put the weights on the platter, and it will weigh correctly. When one of them's cold or one of them's hot, they don't weigh right. And the more electrons you have in something, even though it's hotter, you'd think it'd be less heavy, but it's heavier. When you add electrons in, which is heat, it becomes heavier. When the electrons leave, it becomes lighter, because the gluons, the black part, has all the weight. This has no weight, but this is the one that drags this one around with it to go to where it's hot or where it's cold. All right, this will be pushed away from a hot area, and it will be attracted to a cold area because it will want more of these in that cold area. So anyway, we're going to do neutrinos, muons. I know I'm getting a little confusing, I'm sure, to you, but these are the only two particles that make up everything that exists. And after you put two of them back to back, you have a photon. I'm going to show you the standard model. But we've got this pretty well detailed. And what happens is the dark matter goes to the center. All right, these particles can divide, the black and the white. I never thought you could, but when you get down to this level, there's nowhere else to go. The black is attached to the white, just like here. I'll show you. There it is, right there. That's where this is the smallest particles that exist, because this is light. This came from a laser, and this is exactly what they look at Fermilab. That's the particles from Fermilab. Where is it? Right here. It's the same particles. And they say these are the two smallest particles that exist. This one has all the weight, and this one has all the energy. Right here, it says it right there. In summary, the black particles have a fixed size. They may have a fuzzy edge around them, which is the color. The point-like particles, which is the glowy one, it's an abstract, zero size. But it has a field, and that's exactly what it is. And there they are. And this is exactly what we found in the light. This is light. And these pictures were taken with a CMOS cell phone. CMOS is complementary metal oxide silicates. And you pick up the radiation. All right? And this was done with just a cheap CMOS phone. And we can still get all kinds of pictures with this. I mean, I got a ton of them, an absolute ton of them. And you can see light spinning, you can see light speeding up. The particle is speeding up. Back here, it was in here, which had a big field around it, which was the magnetism, which creates the wave. So they always say, is it a wave or is it a particle? Well, it's both. The particle creates the wave. Now we pulled the particle right out of it because we accelerated just like a jet fighter right out of its, breaking the speed of sound. Well, we're breaking the speed of light. And here it concusses at the Venturi, and then it's just off to the races. This is, like I said, it takes tons of energy to separate these. Well, let's take a look at what Jefferson has to say. Hold on. All right, pay close attention to this. They're going to be talking about gravity off the charts because they never knew what gravity was before. But gravity now they realize is inside the proton, which it is. It's the muon. Now, and then they're also going to be talking about, well, let's just read it. Here goes. Gravity's influence in this is unmistakably evident throughout the observable universe. Everywhere you see gravity attracted to masses. Its effects are observed in the synchronized orbits of moons around planets and comets to deviate from their paths due to the gravitational pull of large stars, and in the majestic spirals of enormous galaxies. These magnificent phenomena highlight the role of gravity, which nobody even can explain, on the grandest scales of matter. Yes. Meanwhile, nuclear physicists are uncovering the significant contributions of gravity at the very smallest scales of matter. The standard model does not explain gravity. I find that ironic. All right, so here we go. New research conducted by nuclear physicists at the U.S. Department of Energy's Thompson Jefferson National Accelerator Facility is using a method that connects theories of gravitation to interactions amongst the smallest particles of matter, which is what I work with, to reveal new details at this smaller scale. All right, I've shown you the details, and I will again. The research has now revealed for the first time a snapshot of the distribution of the strong force inside the proton. Inside the proton is light. When you smash protons together, light comes out. So inside the proton is what I was showing you. And I was showing you the strong force is the white particle and the dark matter is the black particle. So they say it now revealed for the first time, well, we had this in 2015. a snapshot of the distribution of the strong force inside the proton. Showed it. This snapshot details the shear stress and the force may exert on the quark particles. They are not quarks. They're just more and more dipole electrons. So it says the snapshot details the shear stress the force may exert on the quark particles that make up the proton. The result was recently published in the Reviews of Modern Physics. So let's continue on and see what else they have to say. Hold on. All right, this is insights into the proton's structure. Okay, don't forget now, according to dipole flood theory, this is my dipole electron flood theory, there's two possibilities. One is the dark matter goes right to the core and is just surrounded by all kinds of little electron parts. And the closest ones are the blue. The next layer would be the green. That's their energetic values. Now, it could be that, or it could be this, where there's layered. All right, so you'd have the black core, still it would be a certain black core, and then it would be surrounded by a certain number of electrons and made it really stable. And then you'd have another core, another black layer, and then there's those electrons, then another black layer and those electrons. And the reason we never see the dark matter has never been seen, because it's always surrounded by the white particles. Now either they're blue or they're red or they're green, but they are the ones that surround the dark. So when we hit them with anything, it bounces back as light. So we never see the darkness. The only reason we can see them in our stuff when we did these experiments is because the black particles are laying right on top of the white particles, of the white shower. See it? That's the only reason we can see them, because they don't emit, they don't absorb, they don't reflect, and they don't have any other, they don't do much of anything other than attract the white. And I mean the white is just gobbles right into them. They're all over here. You just can't see them. You can't see them. You can see them as the white sort of surrounds them, but you can't see them independently of this kind of an interaction. And again, this is the muon, sterile muon. This is the electron shower. That's what we did. This is fission, and that's fusion. And this should be just off the charts amount of electricity. All right, now listen to this. This is insights into what's inside the proton and the structure of the proton. So, according to the lead author on the study, the measurement reveals insight into the environment experienced by the proton's building blocks, the blocks inside that make up the proton. Protons are built of three quarks that are bound together by the strong force. I totally disagree with that. Now listen to this. This is outrageous, but it's not, I don't disagree with this whatsoever, because to rip that white away from that black, it takes just a zillion, I mean tons, 4 tons of force. At its peak, this is more than a 4-ton force that holds these particles together, that one would have to apply to a quark to pull it out of the proton, to make the white come away from the black. Because that's what they think. The black is the proton, and the white is these quarks. Well, that's not true. So the nature, of course, does not allow us to separate just one quark from the proton because of the property of quarks called color. Well, that's the different neutrinos, basically. They're talking about quark colors. Well, it's neutrino colors, and I will show you this. Anyway, I have pictures of this. There are 3 colors that mix quarks in the proton to make it appear colorless. That's the blue, the green, and the red. So when you see it, you don't see any color. They mix together as white. From the outside, a requirement for existence in space. Trying to pull a colored quark out of the proton will produce a colorless quark-anti-quark pair. Well, I don't know about that. A meson, using the energy you put in to attempt to separate the quark, leaving a colorless proton or neutron behind. So the 4 tons is an illustration of the strength of the force. It is intrinsic in the proton. That's how much it holds it together. It's so solid. You're going to need 4 tons to open it up. That's what they think. No, absolutely not. we can use light. So we don't have to, we're not working with these big gigantic particles. We're working with light. Totally different situation. So they're taking these huge things and smashing them to bits. We already got the bits. And then we're accelerating those bits through the Venturi. And when you do, one of them is a fixed size. It can't get smaller. It can't get through that Venturi. The white gets squirted through. So that's the 4 tons of force they're talking about. And here's what they're saying right now, which we could created electron showers. And I think this is from that lab there, Jefferson Lab. I'm pretty sure this is where I got this from. Proton-proton collisions break down the hadrons, and then they got to do all this and decay, all that stuff. We started right here with the neutrinos. The neutrinos are where we began. All right, neutrinos are just part of the dipoles. All right, that's a muon neutrino, and that's an electron neutrino. We started there. We separated them. That's what exactly what they want to do to create these electron showers. And that we did. Using lasers, not using big protons. They're using high-speed particles going around, smashing them to bits, and then they have a cloud of debris that they dig through forever. And then they did find the particles. And they say, yes, here's the smallest particles that exist. And one of them has all the weight and a little glowy edge, showed you. And that one has no weight and has all the glow. And that one can get big and small, and I can show you that again as well as I did before, but make sure you understand and see. These never change size. They have a glowy edge, depends on what color the electron was, and they're blue, green, and red. Now, these can get bigger, depending upon if they're charged up, or they can get smaller if they're discharged. And that allows them to squeeze through the Venturi where the black one can't get through. The little ones, they can squirt right through. The black one can't get through. So it creates a huge blast at the Venturi entrance. Right here. And the black ones keep slamming against the white ones, and they can't get through. And they push the white ones through. And over here, we should be able to harvest those as raw energy. All right? That's what I'm saying right now. That's what I believe is factual. Now let's go back to see what Jefferson has to say. All right, let's just keep going with this. Like I said, it takes 4 tons, they claim, to break this into pieces. Well, we did it going through the Venturi using no additional energy whatsoever, just harvesting the white now. And we could direct it and shoot it all day long. Now, in the mid-60s, it was theorized that if nuclear physicists could see how gravity interacts with subatomic particles, such as the proton, such experiments could reveal the proton's mechanical properties directly. Yes, the proton is just constructed of all those dipoles. Now, but at that time, there was no way. If you compare gravity with the electromagnetic force, for instance, there is 39 orders of magnitude of difference. So it's completely hopeless, right? No. A Jefferson Lab person asks, is it completely hopeless? Well, theoretical foundations and experimental breakthroughs. The decades-old data came from experiments conducted at Jefferson Lab, continuous electron beam. Continuous electron beam. That's what we use with lasers. Now, a typical experiment would entail an energetic electron interacting with another particle by exchanging a packet of energy and a unit of angular momentum called a virtual photon with the particle. The energy of the electron dictates which particles it interacts with in this way and how they respond. Now, we're just working with electrons against electrons and forcing their fields to repel each other, causing enormous amounts of energy. So they're using, they still want to stay within the standard model and work with protons. Even though they're working with an electron beam, they're going to shoot it into a proton, I'm sure. All right, here it is. In the experiment, a force even much greater than the 4 tons needed to pull out a quark, which is the electrons, was applied to the proton by the highly energetic electron beam. See, they shot it into a proton, into the electron beam, interacting with the proton in a target of liquefied hydrogen gas. All right, so they had liquid, which means it's very, very cold, hydrogen, and they shot this extremely powerful, energetic electron beam in to those protons, which are floating around in there, to try to disassociate little particles. We never got to the proton stage. We never got above this big. This is where we are. They're up here. That's why it's not mobile. So there's so many problems when you're at this scale versus the scale we were on. All right, listen to what they say. They developed a program to study deeply virtual Compton scattering. That's inside the protons. This is where you have an electron exchanging a virtual photon with the proton. So it's like knocking a particle out of the proton. At the final state, the proton remained the same, but it recoiled, it bounced. And you have one real, very highly energetic photon, which I'm showing you. These photons are so energetic, it's unbelievable. Plus the scattered electron, which really is the photons. At the time we took the data, we were not aware that beyond the 3-dimensional imaging we intended with this data, we were also collecting the data needed for accessing the mechanical properties of the photon. So now they realize we got a problem. There's something different about the proton that we can't explain. When we collected this data, they didn't look at it right. But now they realize that there's much more to the proton than a couple of little quarks. But I don't even think they realize it now. All right, let me finish it up with this here. They want to see, is the standard model right? Critical decision clears the way towards standard model test. It is not correct. They're spending a ton of money to look at this stuff, and you don't have to hardly look at all if you look at what I'm showing. These are what they're talking about, the gluons, which are the red, green, and blue particles. And we see all the same stuff, only they are made of dipoles. I've shown you very clearly. Now, and this is what they want to do, moving forward with all that nonsense. And then you can't carry that around. This is what I'm proposing right here. The Venturi shooting through the laser shooting through the Venturi. We harvest just the white, which is red, green, blue, whatever it is, but it's not the black. The black stays out. All you want is the glowy particles. You bring it down, that's what's called electron showers. And I believe this is from Jefferson. I'm not sure, it might be from Lawrence Livermore, but they want to do the exact same thing. They come in, well, here it is right here. These are the electron showers. These are electrons. They come in very tightly packed, and then they're low energy here. They don't have all, but they create huge amounts of energy, high energy, or the cone gets bigger and bigger and bigger, which is exactly what I showed you with ours. Now the muons, which is the black balls, they stay back here. They can't get through. And if my stuff works right, and I think it will, you could carry that around, and I believe something that size could probably power a car or a house or whatever. It's portable and it's completely encased. There's nothing there that can interact with anything. It's 100% secure, and it's 100% non-polluting. It's only working with light, so you can't get damaged. You're not throwing off big chunks of particles like that and getting smacked with those. You're just working with these, started with these, so that's all you're ever going to have. Only we pumped them up so where they lost the black particle and stayed with the white particle. I think I've been pretty clear about showing you what's going on here. And I see no reason we shouldn't be able to get free energy right now. And NASA's saying we want a big challenge of how to create a new engines to run airplanes. All we need is electricity. We got all the motors and everything we ever wanted. We just need the electricity. If we can get electricity for free, it doesn't get much better than that. You don't have to develop anything. What they're trying to do now is develop this gigantic new system well, I'm going to quickly show you and then I'm going to cut it off. Okay, this is kind of crazy. They want to have students designing a new engine system, really, a whole new engine system. Listen to this.
Hi, I'm Dr. Roger Dyson, Lead Electrical Propulsion Technical Engineer at NASA's Glenn Research Center in Cleveland, Ohio. I'm here to tell you about the most exciting invention in my aeronautics career, with environmental impact that could change the world.
All right, they're going to have kids try to design this new engine that they're coming up with to do what they're going to call net zero. In other words, zero emissions. Well, what I just showed you is zero emissions, and they should be able to power airplanes with this. Instead, here's what they want to do. Listen.
Numerous recent technology papers have identified the importance and challenges of achieving a true zero greenhouse gas emission aircraft.
That's electric.
So NASA invented closed-cycle turbogenerator technology.
This is just insane. And they want, I mean, we're talking billions of dollars to get this up and running, to try to figure this out in many, many years to power these things. We already have all the engines, and motors, basically. Electric is motors. Engines are gasoline or some other combustion. So we already have all the motors we need. We just need the electricity. And I think I just showed you how we can get the electricity. If they're putting out this challenge, why don't they just investigate what I'm showing?